Welcome to Power Factor Correction in Distributed Systems. I'm Peter Lillis, and this is my submission for UBC's EECE 492, Energy Systems Management with Dr. William Dunford. During this presentation, I will discuss the basics of power factor correction, how to calculate power factors for purposes of correction. I will explain common types of PFC techniques present in industry, with particular emphasis on correction for inductive loads. The benefit for the consumer and utility are examined. The BC Hydro power factor surcharge will be explained, as well as justification of why it is necessary. Finally, an introduction to how Europe handles PFC on low voltage devices through IEEE standards is presented and compared with North America's approach. So why should we care about the power factor of our circuits? In today's competitive economy, businesses and utilities are taking measures to ensure they use energy more efficiently to maximize the capacity of their systems. Companies need to get more out of their existing infrastructure to achieve better rates of return. Generally, loads such as lighting ballasts, motors, fans, and computers do not have a good power factor. As a project manager or consultant, reducing power factor will lead to a more efficient use of electricity within your system or distribution grid. A more efficient system leads to cost savings in the form of avoiding power factor surcharges, less wear and tear on equipment, lower maintenance costs, and less frequent failures. It also provides an increased capacity of the distribution system, as well as reducing line losses and increasing voltage stability. For the utility, power factor correction by the consumer results in an increased capacity to supply usable power with the existing infrastructure. There are also other benefits, such as the ability to sell power to other utilities if the power factor is above 95%. So what is power factor? Let's begin with an introduction. Power factor is a major consideration in efficient building or system operation. It is the measure of how effectively your equipment is converting electric current to useful power output. It is defined as the ratio of real power to apparent power. It is important to know that power factor is a unitless number between 0 and 1. So now let's look at the three components of power. So here we have the power triangle. It's got the three sides: reactive power, true power, and apparent power. The actual amount of power being used or dissipated in a circuit is called true power, and it is measured in watts and represented by the capital letter P. Reactive power is the phantom power in a circuit. It is measured in a unit called volt-amps reactive, or VAR, rather than watts. The symbol for reactive power is the capital letter Q. The combination of reactive power and true power is called apparent power, which we see on the hypotenuse. It is the product of a circuit's voltage and current, without reference to phase angle. Apparent power is measured in the unit of volt-amps, VA, and is given the symbol capital letter S. Let's look at the three components of the power triangle in greater detail. Real power is the product of the square of the current and the resistance of the circuit. This can be easily measured using a piece of equipment called a wattmeter. Reactive power is the product of the square of the current again, and this time multiplied by the circuit's reactance. It is given the units VAR. And lastly, we have apparent power. It's the product of the square of the current, and this time the circuit's impedance. Alternatively, it can be found by multiplying the voltage reading by the current reading. It's time for a more practical explanation. Let's look at the beer mug example. As mentioned at the beginning of the video, power factor is the ratio of real power to apparent power. The beer in the glass represents the real power, the watts, and the foam represents the reactive power, or the VARs. The apparent power is then everything in the glass, which is the total system capacity. From this analogy, we get the idea that the foam indicates a low power factor. So the more foam, the lower your power factor. Now that we have an understanding of what power factor is, we need to know some sources or loads that have a low power factor. Here are 5 household items that are measured for apparent power and power factor. We see the LCD TV and tower fan have the best power factor, they're close to unity, or 1, and the laptop and wireless telephone have the worst. Only half of the current supplied is being used effectively in these 2 products. So why is this the case? Some products have to meet worldwide standards for PFC. The most stringent standards are in Europe. We will discuss these standards towards the end of the video. Now we will suffice with the explanation that the TV and tower fan are made for a worldwide market, where the other products are intended for a North American market, and do not have to adhere to the same standards. In factories, we will not generally be concerned about PF correction for small household devices. Instead, we may be examining a load of a lighting circuit, or a load of large motors, or even many motors. We can see that many motors operate between 70 and 90% power factor, whether at half load, 3/4 load, or full load. Looking at the relationship between a percent full load amperage and power factor, we notice that the motors operating above 65% full load do not have a significant change in the power factor. This helps to determine that for many motors, we only require a fixed size corrector. So how do we correct for a poor power factor? We have seen that sources of reactive power, inductive loads, decrease power factor. These can be transformers, induction motors, induction generators or windmills, and high-intensity discharge lighting. Similarly, consumers of reactive power increase power factor. These are capacitors, synchronous generators, and synchronous motors. So it comes as no surprise that one way to increase power factor is to add capacitors to the system. Adding capacitors to the system is the most common technique for correcting a poor power factor. It is generally called passive correction and done through installation of shunt capacitors, which are capacitors connected in parallel to the load. The installation of power factor correction capacitors will reduce the kVA demand on the transformer, thereby allowing additional load to be added without transformer resizing. Improved power factor will also help to reduce losses and support the bus voltages. When the need arises to correct a poor power factor in an AC system, you probably won't have the luxury of knowing the load's exact inductance, or henries, to use for your calculations. You may be fortunate enough to have an instrument called a power factor meter to tell you what the power factor is, a number between 0 and 1. And the apparent power, which can be figured by taking a voltmeter reading in volts and multiplying by an ammeter reading in amps. In less favorable circumstances, you may have to use an oscilloscope to compare voltage and current waveforms, measuring phase shift in degrees and calculating power factor by the cosine of that phase shift. Most likely you will have access to a wattmeter for measuring true power, whose reading you can compare against a calculation of apparent power from multiplying the voltage and current measurements. From the values of true and apparent power, you can determine reactive power and power factor. Let's look at an example using this circuit to see how this works. First, we need to calculate the apparent power in kVA. We can do this by multiplying load voltages by load current. As we can see, a 2.308 kVA is a much larger figure than the 1.5 kilowatt measured by the wattmeter. We figure the power factor of this load by dividing the true power by the apparent power. This tells us that the power factor in this circuit is poor. It is substantially less than 1 at 0.65. Remembering the power triangle, we manipulate Pythagorean theorem, given the lengths of the hypotenuse, the apparent power, and the length of the adjacent side, the true power, to find the reactive power Q. If this load is an electric motor or most any other industrial AC load, it will have a lagging inductive power factor, which means that we will have to correct for it with a shunt capacitor of appropriate size wired in parallel. Now that we know the amount of reactive power, we can calculate the size of the capacitor needed to counteract its effects. Rounding this answer off to 80 microfarad, we can place that size of capacitor in the circuit and calculate the results. The 80 microfarad capacitor will have a capacitive reactance of 33.157 ohms, giving a current of 7.238 amps and corresponding reactive power of 1.737 kVAR for the capacitor only. The capacitor's reactive power will directly subtract from the load's reactive power, since the capacitor's current is 180 degrees out of phase from the load's inductive current draw. This correction will not change the amount of real power consumed by the load, but it will result in a substantial reduction of apparent power and the total current drawn from the 240 volt source. In the previous example, we corrected an individual load. There are some advantages to working with only one load, as there are also disadvantages. The advantages include increasing load capabilities of distribution system by reducing supplied current. They can be switched off with equipment, thus no additional switching is required. Better voltage regulation results, and capacitor sizing is simple, as we've just done. Capacitors coupled with equipment can be relocated during rearrangements. The disadvantages can be small capacitors cost more per kVAR than larger units. Economic breakpoint is generally around 10 horsepower motors. Difficult to install in special application areas like flameproof or increased safety. Adding more equipment for maintenance. When the capacitor rating is too high, overcorrection, or more magnetizing kVA of the machine, it may damage the motor and other connected equipment. Not every installation can be corrected directly at the load. In some cases, it is better to correct for a group of loads. Group correction advantages are that increased load capabilities of the service, reduced material costs relative to individual correction, reduced number of equipment for maintenance and easy access for checking, self-excitation of induction motors due to high capacitors is avoided. Cost per kVAR is less than larger units. Demand management is easy, and power factor can be corrected near to unity. These can be installed in substations and hence suitable for hazardous areas. Disadvantages are that switching means are required to control amount of capacitance, as the load generally changes. Individual switches are required. This does not reduce cable losses below the point of correction, and it does not contribute to downline equipment life expectancy or efficiency improvement. Leading power factor on self-generating plants if not switched properly, and chances of switching directly the capacitor loads on power outages. Correcting for groups of loads leads to what is called active power correction. These installations usually are located somewhere near the service connection or in a general area close to the system. These installations can range in cost from $1,000 to $50,000 depending on the required capacity. On smaller circuits such as consumer products, integrated circuits are available at a relatively minimal cost. DigiKey lists active power factor correction modules for around $3.37. The costs associated to correcting your power factor are equipment such as capacitors and switching circuits and installation. The costs vary for passive and active systems. Passive systems range from $15 to $30 per kilovar and depending on the manufacturer. Active systems are generally thousands of dollars but service larger integrated loads. After installing capacitors in our system, should we expect some savings? Yes, let's look through an example of how to figure this out. A calculation can be run to determine when this payoff will be. As an example, assume that a portion of your facility can be modeled as in the figure. Your current power factor is 0.65. The parameters for the system are as follows: 163 kilowatt load, 730 hours per month, 480 volt 3-phase service, 5% system losses, load power factor of 65%, PSC rate schedule of the energy rate at $4.08 per kilowatt hour, demand charge of $2.16 per kilowatt, and a power factor penalty of 15 cents per kilovar. We'll calculate the total amount the utility charges you every month as follows. First, we'll calculate your energy usage. At 163 kilowatts times 730 hours per month at $4.08 per kilowatt hour, it's $4,854.79 a month. Next, we'll calculate your demand charge. 163 kilowatts times $2.16 per kilowatt is $352.08 per month. Finally, we'll calculate your power factor penalty. 190 kVAR times 730 hours. Now let's say you decide to install a capacitor bank. The 190 kVAR from the capacitor cancels out the 190 kVAR from the inductive motor. Your power factor will now be 1, or unity. Now you can calculate your loss reduction. Loss reduction is 1 minus the 65% that you previously had for your power factor divided by the 1 that you now have. And that equals 58%. Therefore, your system loss reduction will be as follows: 58% times the 5% losses, and you get a 2.9% system loss reduction. Your total kilowatt load will be reduced as follows. We now get 163 kilowatts times 0.29, or 0.029, which equals 4.7 kilowatt, and we can calculate our savings in our energy usage as 4.7 kilowatt by 730 hours per month by $4.08 per kilowatt hour. This leads to $141 per month. Next, we'll calculate the savings in demand charge. So 4.7 kilowatts times $2.16 per kilowatt hour equals $10.15 per month. Finally, remember that your power factor penalty is now 0, so you don't get penalized for your power factor. So let's look at the payback period. Let's calculate how long it will take for this capacitor bank to pay for itself. Let's use a capacitor cost of $30 per kilovar. So your savings per month are as follows: $141 for energy usage, $10.15 in your demand charge, and $208 in your power factor penalty charge. These result in a total savings of $359.15. So your payback period will be the $30 per kilovar times 190 kVAR divided by 359 per month, which is 16 months. Installation of your capacitors will pay for themselves in 16 months. Let's look at utility billing. Here is an example of a bill from BC Hydro. We see that the electric, energy, and demand charges, and the power factor surcharge. We've covered how to lower these three charges, but let's examine the PF surcharge. The BC Hydro power factor surcharge. BC Hydro's condition of service requires equipment to have a power factor of at least 90%. On most non-residential service, a charge is applied to cover the extra service needs, determined by the degree of power factor. If you have a low power factor, BC Hydro may do one of three things: disconnect your service, require payment of an additional 50 cents per month for every 100 watts of the connected load, or apply a surcharge to the total bill. The surcharge rates operates on the curve shown. It is an almost linear relationship. As the power factor is worse, the surcharge increases and is determined on percentage of supplied kilowatt hours. So why do we have a surcharge at all? Since BC Hydro does not directly charge for kVA supplied, they do not have a direct means to recoup costs incurred with correcting for a power factor. This means that if you have a poor power factor, BC Hydro is responsible for correcting it to maintain power quality in the grid. This can be very costly to maintain. As we see in the figure, the total kVA includes not only the real power, but the reactive that must be supplied. A greater reactive power lowers the real power that can be supplied through the existing infrastructure. This essentially reduces capacity of the system. When an induction motor, which is the most widely spread contributor to reactive power in a plant, needs reactive power, it is not necessary to draw it from the generators in the transmission grid, but a capacitor near the motor terminals can supply it. This relieves the generator and all transmission lines between the generator and the motor of having to transmit those VARs. Hence, the current in the lines will be smaller than when the capacitor is installed. This will reduce the heat loss, or I2R losses, and reduce the voltage drop in the system. This is good news for the consumer and the utility. Due to many products having a poor power factor, as we have seen in earlier sections of this video, this has caused problems for the utilities, and in Europe it has prompted the passing of 2 regulations. These 2 standards are European regulations that require all electrical equipment connected to a low voltage distribution system to minimize current harmonics and maximize power factor. In North America, a similar standard is now being considered, and this draft has been assigned the following designation by IEEE for control purposes. However, the regulation of harmonic distortion, which was not the scope of this video, requires active power factor correction, and during the discussion phase, consensus is that the requirement of active power factor correction in manufacturing would impose an unnecessary burden on society. Currently, IEEE has not implemented the standard for North America. In summary for this video, we have seen that a method of getting better efficiency of our systems and products is to increase the power factor. We have learned simple methods for power factor correction calculations, and we have been introduced to active and passive systems. We recognize that significant savings can be achieved by optimizing the power factor where there are inductive loads, not only larger loads, but in consumer devices as well. We are able to avoid surcharges by the utility by having a better power factor. We also reduce line losses, and this results in getting more out of your system. Thank you, and I hope this information may be of use in your career.